Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session. And if you have questions, please direct them to me via the chat function. We'll do our best to answer those questions at the end and to follow up with any unanswered questions by email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components. We talk about the related technologies and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and numerous white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So today's format will be somewhat different. We will be posing key questions to Shaun about these ground-based power dividers and power combiners. He'll share his considerations and definitions, maybe do a quick summary, and we wish you all the best for happy holidays. So welcome, Shaun. I guess our first question. I understand that ground-based dividers and combiners are considered the unsung heroes in the RF world because they kind of work behind the scenes to bring about better communication and efficient signal processing. But is this accurate? What's your interpretation of this perspective?
Yeah, thank you, Paul. So I really think that they are. When we talk about new technologies, it's always about the latest and greatest things that are going on. In reality, a lot of passive components like power dividers and power combiners really haven't had very many big technological breakthroughs over the past several decades. Most of what we've been working with now are really subtle, small improvements going on based on other material sciences and based on other sorts of miniaturization and other little bit of power handling and heat dissipation sort of materials that are being developed. So our improvements have been subtle. What hasn't changed is the necessity to take energy and redirect it to where it needs to be. And as a result, it's very often a sort of a piece that is very often neglected until the very end of the design. Everybody always gets excited about the newest, latest, more broadband or higher power amplifier without realizing that, gee, they need to take that amplifier, they need to either divide the power or combine the power for the final use. And parts are very important, but at the same point, a lot of people tend to think about them second.
Okay, so they are somewhat unsung. So maybe you could differentiate, what exactly does ground-based refer to? I mean, I suspect that there are different types of dividers and combiners that are not ground-based.
Sure. So, usually when you get into a ground-based or an airborne or parts for a spacecraft, it becomes platform dependent. What we refer to as ground-based stuff tends to be either stuff for systems that are really either, for example, like an over-the-horizon radar, a ground-based radar, or a satellite terminal, where we're talking about having a large reflector antenna that's going to then go up there and use as a link to a satellite, or used as a data link for any variety of applications. Some of these applications refer to a lot of ground-based military installations where we have to where we have to have communications with either air base or squadrons or submarines or Navy ships, and therefore these communications have to start somewhere, and there's usually a base somewhere where this conversation has to start from. So really the platform for a ground-based operation is usually all that refers to really is that it's a fixed location as opposed to something that's mobile.
Okay, so simply stated, I understand that a power divider splits an incoming RF signal into equal or unequal outputs. Why is this so important?
This is really critical for when we get into building a phased array system, for example. If we're talking about a ground-based radar, where we have to um, build a beam or steer energy into a particular direction without using a reflector antenna. Uh, Theoretically, what these systems require is a uniform phase front coming off of that aperture. And really, so what's important is that we need to distribute energy across sometimes a very large area. And this is one of the differentiators now between a ground-based system versus, for example, an air-based system, is that parts that are on an airplane, for example, are small because there isn't that much room on the plane to really have a large system. Uh, Whereas for a ground-based system, these radars can actually occupy the sides of buildings. I mean, they can be quite large. Uh, and TRM also makes components for some of these over the horizon radars where the baseline for these apertures is literally in miles. So sometimes you get very large structures when you talk about ground-based operations, and you need to divide signals and distribute them across very large physical areas. Therefore, a series of well-matched power dividers is critical for the system operation.
Okay, well, that makes sense. Now, I've also heard you speak frequently about how they provide isolation between the output ports. Can you explain exactly what that means?
Sure. So isolation between the output ports means that if you were to take a signal and inject it backwards through the power divider, the energy would not appear at one of the other outputs. It would naturally pass through the power divider and come out the common port. So really, why is that important? Because if you're in either a receive or a transmit application, the inter-element isolation is critical for beamforming. If we have energy leaking from one element to the other, that will impact the ability to create a pure mode for that particular beam that we're generating, and therefore it will degrade the antenna pattern. Things like grading lobes and things like that can then also be generated through poor isolation within the power divider network. So for a phased array, inter-element antenna isolation is critical for that sort of application.
Okay. Now, as opposed to a divider, my understanding is that a power combiner merges multiple RF signals into a single output signal. And somehow I've read that this enhances overall system efficiency. Can you explain how that happens?
Sure. So for a power combiner now, especially for a ground-based system where you want to get a higher power level, if you don't have, for example, a single amplifier that can generate enough power, if you put two and put them together, you can effectively double your power. Well, in order to be able to do that, you need an efficient power combining network. And that's one of the parts that Quantic TRM does build, is this combining network. So what's important about that is that we generate low loss combining networks, so that we can be efficient at having that total power being delivered to the system without wasting it in heat or non-efficiently combined energies. So really, a big part here of what we're trying to do is being able to combine powers without generating any excess heat, so that we can have a nice efficient power combining happen, and therefore the end use for the ground system is that it's more efficient.
Okay, well, that kind of makes sense. What are some of the most common applications for either the dividers or the combiners?
What we've seen here at TRM is that we use a lot of work on ground-based radar. Really, what we see for a lot of the ground-based radars is that it's different than what we see for some of the airborne radars, is that the use of lower frequencies. Lower frequencies and different frequencies have different advantages, and every Every radar has its pluses and minuses, and depending on what your target is, certain frequencies are better suited than others for identifying that target. One advantage that they have for a lot of ground-based radars is that they can use lower frequencies than what they have, for example, on an air-based radar, because physically the aperture can be bigger than the aircraft, and by doing so, they can have a lower frequency radar, and in that case, for a lower frequency radar, the radar is going to be quite large. In which case, you have to build a distributed signal distribution network. So individual power dividers connected with very long cables can be a very effective method for building those dividing networks.
Okay. And what about some of the key benefits? I mean, I hear people talking about efficiency, isolation, versatility. And can you explain some of these things a bit more?
Sure. So really, whenever you're talking about a system, what efficiency does, for example, is it limits your range, because if you're generating so much power, or whether you're receiving so much power, if you don't have an efficient system and you're generating a lot of loss for a transmit system that generates waste heat and just wasted energy, for a receive system, it raises your noise floor because it raises your effective KTB, which really just it limits your range. Isolation, for example, like I mentioned just previously, is very important for a phased array antenna system, where you're trying to make sure that you had the most efficient aperture you have without having the elements talk to each other in a negative fashion. Isolation can also be important when you're building a power combining network. If your amplifiers are not phase matched with each other, that can be a good way to improve overall efficiency and not generate high VSWRs in your system. Contrary to that, though, if you do have well-matched systems, sometimes non-isolated power combiners can be a very effective way, because you can usually build those with a little bit lower insertion loss than you can with an isolated version.
Okay. Now, earlier you had mentioned technology changes, and certainly the technology seems to evolve at an increasingly rapid pace. If these dividers and combiners are sometimes the last minute thoughts, what impact might this rapidly advancing technology have on the demand for dividers and combiners?
Yeah, I think especially for a lot of the ground-based systems, based on the size and distribution that these systems really sort of drive us to, I think these sorts of components will be around for quite some time. I think that the need to be able to distribute signals will be there for quite some time. I think what's also happening now is that as a lot of other technologies are evolving, what we're seeing here at Quantic TRM is a demand for broader frequency sort of components, and there you having now, I want to say, sort of mixed use apertures, where they're folding more and more bands into a single aperture, which is making a more sophisticated product for our power dividers and combiners for those ground-based systems.
So there's a future.
Yes, absolutely.
Okay. So that's a lot of good information. Is there any overall summary statement or two that you might want to make on the ground-based nature of these, or on these products?
Sure. I think the one thing I think that really is to think about here is that really the platform is what's different here. The actual nature, as far as what the parts are, is very similar to a lot of the other applications that we have. With the ground-based platform, there are some things that are become more critical actually than what we have for an air-based platform or a space-based platform. The parts are just as demanding, however, the needs are different. Usually we're dealing with higher power components, and thermal management becomes very critical with those higher power components. Usually if you have a link budget, usually the higher power end is the one that's on the ground. and therefore they do tend to be higher power than what we get for the platforms that are either on an aircraft or on a spacecraft. So those are some things that are a little bit unique about it. Also, just the physical size of the ground-based systems tends to be larger than the mobile systems.
Okay, well, thank you. And usually at this stage, you share a little bit about some of the key differentiators associated with Quantic TRM and how they might be applicable. Could you maybe want to go through some of these thoughts here with us today?
Sure, absolutely. As with any system that we work with, and with any customer that we work with, Quantic TRM likes to work directly with our customers to find out really what the best trade-offs are, and really to determine what the optimum solution is for your needs. And as part of that, we go through and we're very careful about the design approach that we take, the materials that we select, really to optimize whether it's insertion loss or isolation or VSWR or whatever parameter it is that's most critical for your application. Very often it comes down to not just something like that, but also sometimes it's like things like phase stability over temperature. And whatever parameter that is, we like to go ahead and we'll work through there. Mechanical packaging is also very important, and making sure that we can test these components to make sure that we validate that the part does what it needs to do. And thing also I want to point out here is that Quantic TRM really is a solution provider. We like to work with our customers to figure out what it is that they need, and from there we develop a product with them to make sure that their needs are met.
Okay, well, thank you, Shaun. And we did get one question that I think you may have answered a portion of it, but you had mentioned that the frequencies used for ground-based power dividers and combiners was different than for airborne. What is roughly the difference between the two?
Yeah, so a lot of systems really are the same, but when you get into longer range radars, for example, you want to go with lower frequencies because of the way that the energy reflects around the atmosphere. There are certain advantages to going lower in frequency if you're looking for longer range. So therefore, a lot of the ground-based radars that we see are lower frequency than what we see for a lot of airborne type stuff. That being said, they would love to put these sorts of things on aircraft. However, the array size that you would need in order to work with these lower frequencies is just too large to fit on the aircraft. So therefore, a lot of systems rely on the ground-based systems to then go ahead and communicate the information up to the aircraft for really long range sort of looking out into the distance. But a lot of the communication links and stuff are on similar frequencies. Really, the biggest thing that we see is that there are a lot of things that are uniquely suited for lower frequencies, and they tend to be ground-based only because physically we can have the space to have those larger apertures available.
Makes good sense. Thank you, Shaun, for that. And thanks to all of you again for joining us today. If you have additional questions, we would love to hear from you. You can call our engineering hotline. The number's on your screen, 888-677-6877. Obviously, there's no cost associated with these conversations. And if you are one of our field sales representatives, you know that your calls are always welcome, and you can reach us through the portal as well. Looking forward to the new year. Our next Tech Talk will be on Tuesday, January 23rd, and the topic will be multi-patching. Thank you again, everyone, and thank you, Shaun.
Thank you, Paul.